Jnanam Paramam Dhyayam. Knowledge is supreme.
Now, let me remind you the normalization lemma. What did we prove? We proved that if I have a finite type K algebra A, then I can find an elements there which are algebraically independent, and this extension is integral, and this is the polynomial algebra because they are algebraically independent. So, therefore, just now what we have proved is dimension of this is a affine K algebra. Dimension of A is equal to dimension of polynomial algebra in n variables. And now this integer n is nothing but this n, the number of variables, that also is nothing but the transcendent degree of the rational function field in n variables. So, I will recall little bit about transcendent degree. Okay, so that is what I was saying, that this is one way to compute dimension in case of affine algebra, and which is finite because we are dealing with finite type algebra. So, all that will involve is finitely many variables, polynomial rings, and therefore, it is finite. Okay, so let us recall some basic things about transcendent degree. So, if I have a field extension L over K, and subset S of L is called a transcendence basis of L over K if two things. Number one, K is algebraically independent over K, S is algebraically independent over K, and second, L is algebraic over Ks, K round bracket S. This is the smallest subfield of L containing K and S, or as a field it is generated over K by S. And then what proves that, then one, I will state it as a theorem. It says that if I have a field extension L over K, then one, there exists a transcendence basis. For L over K, and two, any two transcendence basis of L over K have the same cardinality. And this common cardinality is called a transcendent degree of L over K. The common cardinality the transcendence degree of L over K, denoted by TR deg L suffix K. This one has obvious properties. Okay, before I go on to the properties, we should say some examples, see some examples. L over K is algebraic if and only if the transcendent degree of L over K is 0. In fact, in this case the empty set is the transcendent basis. You do not need any set. So, second, if I have a rational function field, L is the rational function field, this means the quotient of a quotient field of the polynomial algebra. Then obviously x1 to xn is the transcendent basis. So, in this case the transcendent degree of k x1 to xn over k is n. Third, if you have a field which is generated over some capital K by some elements x1 to xm, then the transcendent degree is smaller or equal to n. Equality holds if and only if these x1 to xm are algebraically independent. Okay. This is one transcendent base, but you can give another transcendent base also, because you can simply take the powers. Suppose I take integers x1 power r1, xn power rn, this is also transcendent base, that is also easy to check. So, remember here this proof of this theorem about transcendent basis and cardinalities are equal, etc. This goes similar to the theorem where you prove every vector space has a basis and any two bases have the same cardinality, whether finite or infinite. Same ideas work here also. The only difference is very important difference. Usually in a vector space case you say that K is equal to L, right. Here in the definition you might wonder why do I put the second condition like this and not L equal to Ks. It's one should think about it. Okay. One more example which also will be used sometime later, which I prepare here only. So, 4, if you take a polynomial ring in n variables, and if you take what are called elementary symmetric polynomials, in these variables, that simply means you take S1 which is sum of these variables, S2 which is product 2 at a time, that is x1 x2 x1 x3 and so on, summation xi xj and so on, and Sn is product of all S3 is a product sum of the products of 3 at a time. So, these symmetric elementary, these are called elementary symmetric polynomials in x1 to xn. They arose in the study of equations, mainly Galois theory. They arose because there is a relation between the roots and the coefficients of the polynomial, and the roots, these are the precisely the coefficients of the polynomial, right. So, what I want to say is this S1 to Sn, this is a transcendence basis of the rational functions in n variable over k. They are also n in number. So, this is a different transcendence basis. Sometimes it is useful to work with this transcendence basis than the variables. Okay. So, with this I will for today's thing I will stop the consequences, but now I want to talk about the refined version of the normalization lemma. So, that is, this is the refined version of Noether's normalization lemma. It was proved by Nagata in 66 in the his famous book Local Rings. It's published in around the same time. So, I will state for more ideals. So, if you have a algebra, A is a K algebra of finite type over a field K, and suppose I have a increasing sequence of ideals in A, then there exist elements x1 to xn such that 1 x1 to xn are algebraically independent over K, and second A is integral over x1 to xn. This is what we had in the classical version as well, but the third condition is now new. So, it says that for each I1 to R there exists a natural number Hi such that when I contract this ideal Ai to this polynomial algebra x1 to xn, it is generated by the variables x1 to xhi. It could happen that h1 equal to h2, it could happen. So, they are just integers, they are non decreasing. Okay. So, I will be little slow to prove this because otherwise it is too fast. No. So, first I will prove this assertion to the polynomial algebra, and then we will worry about finite type later. So, A is our polynomial algebra in y1 to yn, and I am going to prove these assertions by induction on n. N is the number of variables. If n equal to 0, there is nothing to prove, because if n equal to 0, then A is a field and it is k and nothing to prove. So, I will assume n is positive, and we can also assume that the first ideal is non-zero. If it is 0, then you just, so once it is non-zero, I can choose a non-zero element there, call it x1. Then x1 is not in the field, because we have considered the chain of proper ideals. So, the bigger ideal, the last ideal is non-unit ideal, so earlier ideals also non-unit ideals. So, this x1 cannot be in K, because otherwise it will be a unit, and hence by remember the lemma we have proved in the second lecture, that if I have a polynomial in n variables, then I can make a change of variables, so that it becomes monic in one of the variable. So, I want to use that lemma. So, that will also show that I can find T2 to Tn, so that think of this x1 as a polynomial, and by changing the variables we have seen that that one is integral over the remaining one, right. So, therefore, T2 to Tn, there exists T2 to Tn such that this algebra A is integral over this algebra C which is generated by x1 T2 Tn. So, here I recall the lemma for you. We have a lemma, A is the polynomial algebra, n determinates x is an element in A, x is not a unit, that is not a constant polynomial. Then you can find T2 to Tn such that this is integral over this. You remember what we did? Ti was yi minus y1 power gamma is, and we have chosen suitable gammas, and then that, okay. So, that was the proof. So, we found x1, so that this x is A is integral over this ring C x1 generated by x1, T2 and Tn. Now, let us put A prime equal to A T2 to Tn and contract this chain of ideals, given chain of ideals to this A prime. Then we get a chain, some of them might become equal, what does not matter, and the last, see all proper ideals. Therefore, by induction, because now A prime is generated by lesser number of elements, I can apply induction to conclude that there exists x2 to xn in A prime such that A prime is integral over subalgebra generated by x2 to xn, x2 to xn are algebraically independent, and these contracted ideal to this B prime are generated by the variables. That was the third condition in the proof. Now, you put B equal to B prime and x1 generated by B prime algebra generated by x1. So, we have a chain like this, A contains C and contains B. These are integral extensions. This is integral by, because A prime is integral over B prime, and this is just a base change because I have adjoined only the x1. So, these are integral extensions. So, therefore, composite is integral. So, that means A is integral over this. This proves 2. 2 is what? Integral, and we still have to prove 1, that algebraically independence we still have to justify, but that is obvious again, because you see x1 to xn I want to show that they are algebraically independent. Now, look at the quotient fields. Quotient field of A is a rational function field in n variables, quotient field of B is rational functions in x1 to xn, and the transcendent degree of quotient field of A is n, but this is integral, therefore, the transcendent degree will not change. So, it is n. So, that means they must be algebraically independent, otherwise transcendent degree will be dropped, right. So, we have proved 1 and 2, and now we want to just prove 3. That means, the contractions are generated by x1 to xhi. Now, x1 we have chosen, x1 was chosen in A1, the ideal A1, and x2 to xhi are in AI, and I want to prove this actually equality here. So, one inclusion is obvious by the setup. To prove the other inclusion, I have to prove that every element which is here is also here. So, start with an element here f and write this f is in B. So, f is a polynomial in x1 to xn. So, this polynomial I want to split into two parts. The first part is the one which involves x1 and the other part is free from x1. So, collect all the monomials which involve x1 and the remaining one which is free from x1 you put it in the other part. So, therefore, any f I can write it as x1 times some polynomial in x1 to xn plus some polynomial in x2 to xn. Now, you see here x1 was already in ideal A1, so it is in every ideal. So, this x1 is there and by assumption f is there, we started with f in this ideal, x1 is already there and f is there, therefore, h is there. So, H of x2 to xn belong to this contraction ideal, but this ideal is same as A prime, AI prime, B prime, and by induction hypothesis this was generated by x2 to xhi. So, therefore, H x2 to xn belongs to x2 hi, because x1 is already there. So, this proves that f equal to x1g plus h, which belongs to this, and we are done. So, that proves this refined version of normalization lemma for the polynomial case. I would like to take a little bit gap here to ask you if it was okay, or shall I repeat some part? Sorry? Why do we need to define it? Because you see, it is always better to have a description of ideal which is generated by the variables. See, instead of studying ideals in a polynomial ring where you do not know what the generators, the structure of the generators, this way you can actually deal with the ideal generated by variables, which are more easier to deal with for calculation purpose. Also, some of the earlier observations also, if you use a more general version, it will become easier. For example, when we prove the dimensions are equal, if I directly apply the third part to the ideals, prime ideals, then it will also tell you that dimensions are equal. Of course, we use the integral extensions, etc., but this will also tell that proof, they tell that the dimensions are equal. Okay, so shall we continue this? So now I have to prove that the general case. The general case is not so difficult. So general case means we are assuming now that we have proved statements 1, 2, 3 for the polynomial case, and we want to deduce it for arbitrary affine algebra. So anyway, every affine algebra, there is a surjective map from the polynomial algebra to the given algebra. And now, given chain of ideals, I am going to contract it. So, the chain of ideals were in A, so I am going to pull it back to the polynomial algebra. So, I will get a chain, and also I will get one more element in the chain, the first one, that namely the kernel, because once I pull it back, all of them will contain the kernel. So, kernel will be another ideal here, which I call it A naught prime. So, the pull back chain now is A naught prime contained in A1 prime contained in AR prime, and now I apply the earlier case to this chain. So, that means we can find the variables x1 to xn algebraically independent. So, that A prime is this one, is integral over this element k x1 to xn, and AI primes contracted to this is generated by this part of the variables, and now I just have to push it. Remember here A naught prime, this starts with 0, A naught prime contracted to this k x1 to xn is generated by x1 up to x h naught, and the A1 prime, for example, will be contracted to h1. h1 is bigger equal to h naught, so it will be later than this, right. So, therefore, you just look at this commutative diagram. A naught prime is here, this is y1 to yn, this is a surjective map, and then all these are integral extensions. This ideal is generated by h naught here. So, when I go mod in this polynomial ring, you start with h naught plus 1 and so on. This is just this is generated by this, and this ring is what we found, and this is just pushing up. This is just A is nothing but this quotient this one is just nothing but this quotient this, and you just pushed on the problem here, and that is easy to check that this AI intersection B, now B is this, that is Now the variable will start numbering from h0 plus 1 etc. There is no new idea involved here, just have to check.